Everyone, I'm Samuel Tapp. I'm working at Damien, and this is the FHE implementation session. And Damien is going to talk about a new CKKS bootstrapping algorithm. Damien, the floor is yours.
Thank you, Samuel. So this is a joint work with Jean-Ki Chen, Guillaume Enro, Jongmin Kim, and myself. So the paper is on ePrint, has been posted 2 days ago. Okay, so let's start. So the main result, the main takeaway is a completely new bootstrapping algorithm for CKKS. It has two important properties that I will focus on after describing the algorithm. Small multiplicative depth, and in particular, we can make it work in a significantly smaller ring LWE ring degrees. And it has high grain parallelizability. So there are many different tasks at a very high level that don't have to communicate to one another for a very long time. So it works well in a multi-threaded environment. Okay, so here is the usual situation with FHE. We have a client that wants to delegate computation to a server while protecting the confidentiality of its data. And there is a general blueprint by Gentry for building an FHE scheme. You start with an encryption scheme that has some homomorphic properties, or which is homomorphic for some circuits. And then what you need to do is to find a bootstrapping algorithm. And a bootstrapping algorithm, it's a specific homomorphic algorithm which computes the identity function. So it takes a plain text, it takes a ciphertext for some data, and it gets another ciphertext for the same data, but which allows to extend the computations. And if it can allow to extend the computations, then you can get FHE or homomorphic computations for all circuits. And for all known FHE schemes, bootstrapping drives the cost. So that's the limiting factor for the efficiency. So that's what we are going to look at during this talk, how to perform bootstrapping. So I'm going to focus specifically on the CKKS scheme, where clear texts are vectors of complex numbers in C to the n over 2, where n is a ring LWE ring degree. So think of n being, in the case of conventional CKKS bootstrapping, it could be 64,000, 2 to the 16. So you have complex numbers up to some precision. And the plain text, so there is we differentiate between clear text, which represents the actual data, and plain text, which is the stuff that we use to encrypt. Plain text are ring elements in Z of X mod x to the n plus 1, and you go from plain text to clear text via the DFT, via the discrete Fourier transform. So ciphertext are pairs of elements in RQ, ZQ of X mod x to the n plus 1, of the form AB, such that when you decrypt with the secret key S, AS plus B is close to the plain text M. Okay, and here in this talk, the secret key will be ternary, and sometimes I will have much stronger assumptions on the secret key. And the plain text is very small compared to Q, because otherwise you wouldn't be able to decrypt. Okay, so what kind of operations can we do with CKKS? We can multiply component-wise the clear text. So we have vector complex numbers, and I can do a homomorphic multiplication. And what it does is that it multiplies two plain text vectors of dimension n over 2, coordinate by coordinate in parallel. So this consumes one multiplicative level. Or, put differently, decreases the ciphertext modulus Q. We can add in parallel and do complex conjugation in parallel, similarly, but these ones are nicer in the sense that they don't consume any kind of level. So they maintain the ciphertext modulus, and you can take a vector of complex numbers and shift everything by, I don't know, 17 positions, and whatever falls out of the range, you put it back. So this we call rotations. They don't consume any level, these rotations. So they also maintain the modulus. So as you can see, we have these levels that we lose every time we multiply. And at some stage, we cannot decrease the modulus arbitrarily. So we end up with a very small modulus that we cannot decrease anymore, and to re-increase the modulus, we use bootstrapping. So the goal of bootstrapping in CKKS is to regain levels or increase modulus. Okay, so if we consider the latency of the CKKS bootstrapping, for typical parameters, say a ring degree of 2 to the 16 with one core, it takes about 9 seconds. But then if you increase the number of cores, you can decrease a little bit the latency, up to 1.1 seconds with 32 cores, and then you can keep adding cores, and then it doesn't help anymore. If you want to decrease the latency, which is the topic of this talk, you can decrease the ring degree, say to 2 to the 15, but then you cannot compute much with this anymore. You have one non-bootstrapping level for actual computations. But this allows you to decrease the latency because the ring degree is smaller, the modulus is smaller, and you can get down to 0.6 seconds for 32 cores. So how does conventional bootstrapping work? So we start from a ciphertext with a small modulus, and we want to get a new ciphertext A prime B prime that also decrypts to approximately M, but for a much larger modulus. So it has 4 steps. S2C, which is a homomorphic inverse DFT. This one consumes 2 or 3 homomorphic multiplication, 2 or 3 multiplicative levels. Then we have mod raise, which is a step that increases modulus. So we simply view AB over mod Q0 as AB mod capital Q, where Q0 divides capital Q, for a plain text which is of the form M plus Q0I, where I is an integer polynomial. But now this changes the plain text, because the new plain text is M plus Q0I. So the next step is to do a homomorphic DFT, which we call coefficients to slots, C2S, again 2 to 3 levels. And to remove this I coefficient, we have this eval mod function, whose purpose is to remove I, to get M out of M plus Q0I, and which consumes around 10 levels, say 8 to 12, depending on how you implement it. So in total, you have many levels just for bootstrapping. Modulus is consumed for bootstrapping. So high modulus consumption, because you need a very high modulus to start with for security, you need to increase the ring LWE ring degree. So you need to take a large ring degree. And because you have high modulus and high ring degree, you end up with a high latency. Okay, so here is the start of the new algorithm. So we start from a new equation to bootstrap. So we have the same input, AB, AS plus B is equal to M mod Q0. And then my intermediate goal is to find A prime B prime at a higher modulus that decrypts to this quantity the DFT inverse. So that means I have in the slots, I have omega to the M0, where this is the first coefficient of M, omega to the M1, the second coefficient of M, up to omega to the Mn-1, where omega is a Q0's complex root of unity. So I can do this because CKKS works on complex numbers, so I can play with the roots of unity over the complex circle, the complex unit circle. So this is my goal. So why is this an interesting goal? So it's actually sufficient to bootstrap, because if you look at the imaginary part of omega to the mi, it's the sine of 2 pi mi over Q0. And when you set parameters correctly, m is small compared to Q0. So sine of 2 pi mi over Q0 is essentially 2 pi over Q0 times mi. So you, by taking the imaginary part, which you can do with homomorphic complex conjugation, by taking the imaginary part, you can recover the plain text, a scaled version of the plain text. So then you have to remove this bit, but you get a scaled version of the plain text. So if you can do this, you can get a high level encryption of the coefficients of M. Okay, and here the coefficients are, M is in coefs, where here we are in slots. So if you want to go from slots to coefs, you can do S2C, which is a homomorphic DFT or inverse DFT. Okay, so there is a small issue here, in that we have only n over 2 slots, but I have n coordinates in this vector, so let's ignore this for the talk. There is a way to handle this. Okay, so now I have my omega to the mi in the I slot. So this is what I want to compute. So what is omega to the mi? It's omega to the as plus b and the i's coefficient of this. And that's, I mean, that works out nicely because omega is a Q0 root of unity and as plus b is defined mod Q0. So it interacts nicely. And now I can write this as omega to the bi plus the sum over j of some a j minus I sj, where j minus I is defined mod n, just by looking at the definition of polynomial multiplication modulo x to the n plus 1. So to compute the vectors of omega to the mi's, I can do a component-wise product, which is a legitimate CKKS homomorphic operation, between the vector of the omega to the bi's and a bunch of vectors that corresponds to the omega to the j minus I sj. Okay, so this one is not going to be too hard to compute, and this one I will explain how to get this one in the next few slides. So once you have this, it's a binary, you can end with a binary product tree, and if you choose S to have small Hamming weight, you can have a binary product tree with a small number of levels. So in this paper, in this work, we use Hamming weight 31, so that you have 1 plus 31 terms and 32 terms, and you can do the binary tree with only 5 levels. Okay, so there is another bug here, another technical issue, in that we do reduction mod x to the n plus 1, and when you do this, it adds signs, so there should be a sign here that depends on j minus I mod n, whether you wrap around or not. It's very painful to deal with technically, but it's not very interesting at a high level. I should mention that there is also a similar bootstrapping strategy considered in a concurrent work by Coron and Kostler, which was also posted on ePrint fairly recently. And this concurrent one is similar up to this point, and starting now, I mean, the techniques to actually compute these terms, they differ. Okay, so now I want to compute those terms. Okay, so to simplify a bit my life, I'm going to, so S is a vector of dimension n with Hamming weight h. I'm going to assume that it has one non-zero entry in every n over h block of coordinates. Okay, it's a simplifying assumption. So in the paper, we are a bit less crude on this one, but for explaining, it's sufficient. So now if you do the component-wise product in a block of these terms, there is only one term that contributes, because only one sj is non-zero. Okay, so you can rewrite this as a sum, because in the sum, because almost all of the sj's are 0, there is also only one term that contributes. You can rewrite the product as a sum. Okay, and now, if you look at this term, it's basically a matrix vector multiplication, where this is a clear text matrix, because the aj minus i's you have in clear, that's given by the stuff that you want to bootstrap. And you can have encryptions of the SIs, which are the secret key material. So you do a matrix vector product, where the matrix is in clear, the vector is encrypted. So this has some advantages, this approach. No level consumption, it's only additions. No plain text, ciphertext multiplications, they also don't consume, they consume one level, sorry. And the operations are simple. The drawback is that the key size is going to be quadratic in n, in capital N, and the cost also. So it's a bit cumbersome. So we have another approach based on what we call blind rotations, where the purpose is to take the vector of the omega to the AIs, okay, and this vector of the omega to the aj minus I is just a rotated version of the vector of the omega to the AIs. So I want to rotate by a given quantity, but this quantity is hidden. It's given by S. Okay, and the way we do it is that we decompose the non-zero entries of S in binary, and we encrypt the bits of these indices, of the non-zero entries of S. to rotate, to blindly rotate by 2 to the 0 index or not, blindly rotate by 2 to the 1 index or not, and so on and so forth. So here also no level consumption, linear key size, and quasi-linear key size, quasi-linear cost. So this is significantly more efficient than the previous method. But the operations that we have to do are more complex. And in fact, so just CKKS rotations do not suffice for this, and we have to tweak CKKS rotations to incorporate the bits of the indices of the non-zero entries of S inside the rotation keys. Okay, so now what is this bootstrapping algorithm at the high level? So for every non-zero entry J of S, I blind rotate the vector of the omega to the AIs by J positions. And then I do a binary multiplication tree to compute this component-wise product. And finally, I perform an homomorphic DFT to get back to coefs. Okay, so there are 3 main steps: blind rotations, binary product tree, and homomorphic DFT. And if you want to get more fun, I refer to the paper we can have, where you can have all the gory details on how you deal with the number of slots which is not enough, the reduction mod x to the n plus 1, which gives you signs, the coefficients of S, which can be not just 0 and 1, but also -1, and so forth. Okay, so let's analyze. This step 0 level, this one 5 levels, S2C 1 or 2 levels. So instead of having 15 to 20 levels as in conventional bootstrapping, we have 6 or 7 levels. In terms of parallelizability, this step is the most expensive one. It's performed H times, where H is the Hamming weight of the secret key. These H things, they are totally independent. So if you have 31 machines, you can put 1 computation on every single machine. And in terms of performance, so as a result of the lower depths, you can take smaller ring degrees. So we went down to n equal 2 to the 13 instead of the previous record choice of 2 to the 15 in a general situation. So the precision is decreased, so that has a cost on precision. And as you can see here, so this is the N13 timings. If you have 32 cores, you end up with a bootstrapping for 2 to the 13 coefficients in 200 milliseconds. And if you want to bootstrap bits instead of small precision real numbers, you can get down to 170 milliseconds. Okay, so just to wrap up, we have a new bootstrapping algorithm for CKKS. It has small multiplicative depths, concretely just 6. We get full slot bootstrapping in ring degree 2 to the 13, thanks to the small depths. And it has high grain parallelizability. So if you have 31 independent machines, you can put the dominating part of the bootstrapping cost into 31 different machines. And this is it. Thank you for your attention.
Is there any question for Damien? Maybe a small one. How does the blind rotate relate to the TFHE one?
Yeah, so it's the same terminology. So in TFHE bootstrapping, you have a blind rotate, and we have a blind rotate, but they don't do the same thing. So in TFHE, you encode a monomial in coefficients, and you rotate the monomial, giving it, transforming it in a new monomial. Here you have so our blind rotations, they operate on slots, and they operate on whole vectors.
Okay, thank you.
Okay, thank you for the great talk. What would be the bootstrapping key size if we use this technique?
It's pretty big.
Sorry?
It's pretty big. So I don't remember exactly. It's I'm going to say something wrong. So you need to look at the paper.
Oh,
it's similar to conventional bootstrapping. Even though the ring degree is smaller, the key size is still similar.
So we need like more keys, right? Like more number of keys?
The key material is pretty big. Huh?
Okay.
Because for every non-zero coefficient of S, you encrypt the bits of this of the index of this coefficient one by one. Huh?
I see. Thank you.
Well, if there is no more question, let's thank Damien again. And now Michael is going to present some results on dealing with very small failure probability in FHE schemes.
Okay, thanks. Yes, hi. So this is joint work with Olivier, Mark, and Nigel. And first up, a disclaimer. The title says homomorphic encryption schemes, like FHE schemes, but we'll be mostly focused on TFHE. So it probably should say TFHE. But everything I say should carry easily to all FHE-like schemes, like FHE and final. And we believe there are probably applications in other schemes as well, but that remains to be explored. All right, let's start out with a little bit of motivation, very high-level motivation. When you deploy a cryptographic scheme, you usually have a trade-off between efficiency and security. And you select your parameters sort of to fit your needs, right? To reach a certain security level, and then this yields a certain performance. And the bigger the higher the security level, usually the less performant your scheme is going to be. That's usually the nature of it. With FHE, there's another wrinkle in here, which is based on the fact that all FHE schemes that we know at this point are based on the concept of noisy ciphertexts. And this noise usually increases during homomorphic operations and needs to be managed through, for example, bootstrapping. And depending on your parameters and how you manage your noise, there might be a small probability that your decryption actually fails, that your noise actually overflows into the message and the decryption actually yields the wrong result. Now, depending on your application, you might actually be fine with like a small probability of failure. And so this seems to give this gives you another dimension in the trade-off that you often don't have. So now you have a trade-off between efficiency, security, and correctness, actually. And then when you do this, there are some natural questions that arise. So generally, it's like, okay, the decryption failures, how does this impact security? And then also, like, can we find some like low overhead measures to sort of reduce the failure probability, and how does this then impact the security? And so to look ahead a little bit, recent years have essentially answered the first question, and this work is mostly about the second and third question. Okay, so since it was in the title, let me explain briefly what we mean by drift. So the drifting is sort of a pun on the ciphertext drift. And the ciphertext drift is usually a component of the noise in the ciphertext that arises due to what we call a mod switch. A mod switch is an operation that is part of the bootstrapping. And the mod switch takes an LWE ciphertext that is defined with respect to some modulus and maps it to a ciphertext that is defined mod some other modulus. And generally, like, the basic idea is very simple. You essentially just scale your ciphertext. And if you were to do it over the reals, like, everything would work out as you wish, and the noise would just scale accordingly. But because you need the result to be integral, you need to round the target ciphertext. And that now introduces some rounding noise. And that is exactly the noise that we refer to ciphertext drift. And so, and especially for FHE-like schemes or like TFHE, this drift is actually a major source of error. Like it sounds like a small rounding error, but it's actually like a major source of error, and it drives the failure probability in TFHE quite a bit. And as recent years have shown, actually, this can actually have a security impact. And so this is a good target to consider when you try to improve the failure probability. So yeah, let's go back to discussing the security of FHE and the correctness, how it relates to correctness. And the standard notion that you consider in FHE is in CPA, mostly because CCA-style definitions are either very hard or impossible to achieve using FHE, depending on which flavor you're looking at. And so, like, the traditional notion seems reasonable, the NCPA notion, which essentially states that ciphertexts by themselves don't leak any information about the underlying message. And in that setting, when you deploy FHE, you either have to assume that your server is passive, like, or is not behaving maliciously, it's just like honest but curious. And you can be fine with this assumption, or you have to embed it into a higher level protocol that essentially forces the server to behave honestly. But then in a Eurocrypt paper in 21, Lee and Michianchu observed that even if you are okay with like passive servers or like passive adversaries, there are natural applications for FHE where NCPA is not enough. They might be vulnerable even against passive adversaries in certain applications, and so they introduced this NCPAD model, which extends the model by giving the attacker access to a decryption oracle, and that almost sounds like a CCA-style definition, but this access is actually very restricted. And it's restricted sort of like you can intuitively think of it as the adversary gets to query ciphertext to this decryption oracle, but only for ciphertext where it should already know the plain text. And so if your scheme is like fully correct, this oracle, or this decryption oracle doesn't do anything to the adversary, like for the adversary, because it already knows the underlying message. And here you can see how it relates to correctness, because if the scheme is not quite correct, has a small failure probability, or is approximate, then the attacker actually learns something new. And this new knowledge can actually lead to devastating attacks. Originally, it was shown for approximate schemes like CKKS, but then later extended also to exact schemes with failure probability. And so failure probabilities actually are also a security issue. And finally, there's another model that we actually introduced in this work, which is a strengthened NCPAD model, because we observed that there are some natural applications where even the NCPAD model is not sufficient. So we actually strengthen it slightly, but I won't discuss as much in this talk, so I encourage you to look at the paper for this. Yeah, and so to recap quickly, we have FHE is based on these noisy ciphertexts, and the noise sort of accumulates during homomorphic operations. So you need to manage this. You usually do this through bootstrapping. Bootstrapping includes a mod switch, and the mod switch, actually increases the noise again, and so drives the failure probability up. And so this can lead to practical attacks in certain applications where you need to rely on the NCPAD security. And yeah, so again, ciphertext drift comes from modular switch. And just because you're secure against NCPA adversaries doesn't mean you're secure against NCPAD security. And so now this leads to the natural question, like, can we reduce the failure probability that is due to the ciphertext drift? And that's where our work now comes in. We have two main results. One is separation between, we introduce this new strengthened NCPAD security, and we separate it from NCPAD. So we give a scheme that is NCPAD secure, but completely insecure in this new model. And we introduce a new model switching method that allows to better control the noise, the ciphertext drift, and this reduces the failure probability. And you don't really need to adjust any of the other parameters, so you can just drop this in as a replacement for the normal mod switch, and also it has like no noticeable overhead in terms of performance. And so let's look a little bit at the details. So yeah, as I said, like we are focused on TFHE, so we have LWE ciphertexts. We have as an input a LWE ciphertext that is defined mod Q. And the output of the mod switching is in ciphertext mod 2n. If you know TFHE, you'll know where the 2n comes from. If not, just consider it a different modulus, which is much smaller than Q. And as I said, the operation is essentially just a linear scaling, but then at the end you need to round. So if you were just to scale, things would sort of naturally scale. but since you need to round, there's an error. How large is this error? Well, you can compute it by simply rewriting the original ciphertext in terms of the mod switch ciphertext and the rounding off terms. And then when you write out the equation, you'll see that the error is exactly this part, right? It's the component that you rounded away, and then there's this linear combination with a secret key. Okay, so what you should notice right away is, well, there's a secret key here, so when you do the bootstrapping, you don't have the secret key, obviously, so you can't compute this drift vector. But there's two key observations here. One is that LDB ciphertext can be almost trivially publicly re-randomized. This is a known fact that is used all over the place, and the idea is to just simply add encryptions of 0. And that's very cheap and very easy to do. And the second observation is, while you cannot compute the drift error, you can compute the drift vector. And the drift vector is what we, denote by these rounded over, these terms that we rounded away. We call this a drift vector, and this can be publicly computed. Right? And so what you can do is the idea is actually now like super simple, is you just look at your ciphertext, you look at the drift vector, and you check if it's like a nice drift vector. And if it's nice, you continue with your mod switch. If not, you just re-randomize it and check again. And you do that until you find a nice looking drift vector. And so the main question now is, what does a nice drift vector look like? How does it impact the failure probability? And how often do you have to check in order to find a vector that looks nice, or a drift vector that looks nice? So these are the three main open questions in this approach. And so let's start with, what does a nice vector look like? And the basic idea is the following. You have a fixed ciphertext now, and associated to that is a fixed drift vector. And this also has a associated drift error that you can't compute, though. But you can compute the expected value and the variance of the drift error, and this gives rise to sort of like a distribution of the drift error. And we assume it's a normal distribution, and then we can use tail bounds on the normal distribution to analyze the failure probability. And so the standard approach here is to analyze this in terms of how far, like what's the probability of a sample from this distribution falling outside like R times the standard deviation of the mean. And this drops off exponentially. And so this allows you to set the error probability by choosing an appropriate tail cut parameter R. And so naturally from this, our test arises, like what does a nice drift vector looks like? So it essentially, a nice drift vector is a vector for which this inequality holds. So, and this sort of like follows naturally from this. So we first answered the second question actually, how does this impact the failure probability? And from that we derive, okay, what does a nice drift vector look like? Right, and so for a given R and given T, you can check this. The question now is, okay, how often do you need to try in order to find a drift vector, or like a ciphertext that has a drift vector that actually satisfies this equation? And that is actually quite tricky to analyze. So this is fairly involved. Up to this point, everything was relatively simple. Now this is where this is quite involved. But yeah, and it's important to analyze this, right? Because if you can't bound the number of times that you have to run this, then your approach might be useless, right? Because it might take too long. You might be better off just increasing the parameters to get rid of the drift error. Okay, so I'm not going to go into the details of the analysis because it's, as I said, it's fairly technical. But sort of just as an example, we looked at some parameter sets and checked how does our approach affect the failure probability. And it turns out for like typical parameter sets, here are two for FHE that were designed to satisfy a failure probability of 2 to the minus 64. And you'll notice that 2 to the minus 64 is not cryptographically secure. Like you wouldn't consider this cryptographically secure. So these are not in CPA-D secure parameters. But by dropping in our new model switching method, you can push this down to 2 to the minus 128 without adjusting any of the other parameters. And the number of trials that you need actually to find good drift vectors is actually fairly low. Like 50 to 100 is like, you don't notice this in terms of performance compared to the rest of the bootstrap. So, yeah, so as a general takeaway with our technique, you can actually, roughly, you can expect, if you have parameters that achieve an error or failure probability of 2 to the minus kappa, our approach allows you to roughly achieve 2 to the minus 2 kappa failure probability without any performance overhead, essentially. Yeah. And obviously, like the exact drop in failure probability will depend on your parameters, but it is always pretty significant, at least in all instances that we've seen. Right, so to conclude, we looked a bit closer at the ciphertext drift and FHE because it's a major source of failure probability. We designed a new model switching method and analyzed it to reduce the failure probability essentially for free. And we also introduced this new strengthened NCPAD model and separated it from NCPA. And for details, please look at the full paper. And to finish up, just a quick remark. So it is my name up there on the slide, but originally Mark was supposed to give this talk, but he couldn't make it last minute. So credit for the slides goes completely to Mark. He made the slides, so not my work. Okay, thank you. With that, I'm happy to take questions.
Is there any question for Michael? Is the technique implemented somewhere already?
I'm glad you asked. Yes, it's in the TF-HERS library. Okay. All right,
No more questions. Let's thank Michael again.
Thanks.
And now Jehan will talk about a new and efficient way to do ciphertext multiplication. The floor is yours.
Okay, thank you, Samuel. So, hi, I'm Jaehyun, and today I'll be presenting ciphertext matrix multiplication for large matrices. Okay, so here's a brief summary. So in this work, we present like fast ciphertext matrix multiplication, which we call CCMM in this work. So like the main result is we reduce CCMM to PPMM, the plaintext matrix multiplication, and our algorithm takes like 1.5 minutes to multiply two large encrypted matrices of dimension size 4,000 by 4,000. And we also have like fast ciphertext matrix transpose algorithm for large matrices. And also we have like lightweight algorithm, which is a variant of those algorithms with a slightly degradation of the efficiency, but require like much smaller key size. Okay, so why matrix multiplication? So actually, privacy preserving machine learning is kind of like one of the killer applications of FHE or homomorphic encryption. So that means like we want to do task in the encrypted state. And during that, as matrix multiplication is kind of like central task in machine learning algorithms, matrix multiplication on encrypted data is kind of like necessary for the fast privacy preserving machine learning. So while doing that, we need to address like several types of matrix multiplications. Some of them are between clear text matrices, and some of them are multiplication between like plain text and ciphertext matrices, and some of them are CCMM. And also like as you want to consider like large machine learning models, like large language model or ChatGPT or something, then you need to address like diverse dimensional matrices. Sometimes they are really big. Okay, so then let's see how fast can we do. So for plain text matrix multiplications, we have like lots of highly optimized open libraries for that, so which we call BLAST libraries. And it depends on the machine, but in my machine, compared to my C++ implementation, they were like faster by a factor of like 30. So they are really fast and really optimized. And in case of PCMM, so last year, a BCHPS paper present a reduction from PCMM to PPMM, and they also present lots of optimization. And to put it all together, now the cost for PCMM is kind of comparable to PPMM, up to a small constant factor. However, for CCMM, most of existing implementation of CCMM are based on JKLS or its variants. Actually, there are lots of variants of JKLS. So they have good bit complexity, but in practice, their implementation, so compared to the clear text matrix multiplication, their latency is kind of orders of magnitude slower. So that means in terms of scalability, so they're good for small matrices, but in terms of scalability, their result is not that desirable because for the same dimensional matrices, it takes tens of hours to do CCMM. So this is not very good because when we want to use FHE for large language model or large machine learning model, this means that the CCMM would be the main bottleneck to implement it with homomorphic encryption. Okay, so in this work, we try to solve this issue. So we are focusing on ciphertext matrix multiplication, CCMM. So we are given two encryption of matrices, U and V, and our goal is to obtain the encryption for the product matrix. And in this work, we focus on ring-algebra-based FH schemes, mostly CKKS. And the reason why we focus on CKKS is that we want it to compatible with other machine learning tasks, and we want high efficiency in terms of throughput. So that's the reason why we focus on CKKS scheme. And also in this work, we focus on large matrices, like this. Okay, so before delving into detail, I want to briefly introduce CKKS scheme. So in CKKS, each ciphertext stores a vector of real numbers, and the CKKS scheme natively supports component-wide addition and component-wide multiplication. And to move the data across the float inside a ciphertext, you need to do rotation, which is related to key switching operation and kind of heavy. So it is possible to just implement PCMM or CCMM by using native operations, but actually when you think of the matrix multiplication, you need to move the data inside the ciphertext a lot. So that means you need lots of rotations to implement PCMM or CCMM based on native operations. So for example, JKLS, the paper have some really good bit complexity, but in practice, their implementation is, compared to the clear text matrix multiplication, their latency is orders of magnitude slower. So maybe the question from my side was that, can we do as fast as plain text matrix multiplications? So for example, how can we utilize the high efficiency of existing BLAST libraries for the encrypted matrix multiplications? So in BCHPS paper last year, we answered this question by suggesting a reduction from PCMM to PPMM. So instead of directly implementing PCMM or PCMM by using native operations, we convert the problem into plain text matrix multiplication problems, and we solve this. We complete this PPMM by using super fast BLAST libraries, and so it will just improve the efficiency a lot. So in this work, we just want to do the same thing for CCMM. So our goal is to make a reduction from CCMM to PPMM so that we can fully utilize the high efficiency of BLAST libraries for the sake of CCMM. Okay, so to do that, so what we want to do is do linear algebra with ring algebra-based ciphertext. So actually, it is very useful to understand the ring algebra ciphertext structure using linear algebra to do that. So here's it. So usually CKK ciphertext is a pair of ring element A, B, where AS plus B equals M. And that actually is equivalent to the following linear equation here. So you can check it by verifying each entry. So this is kind of linear equation with some structure. So here, this kind of anti-circular matrix, we call Topless matrix, have some structure on this equation. So this is kind of equivalent relation that if you have some ring algebra ciphertext, then you can understand it as the structured linear equation. And conversely, if you have some linear equation like this, you can construct ring algebra ciphertext a comma b that decrypts to m. And if you have like several ciphertexts, then you can stack those linear equations vertically to get some matrix equation like this. So this means that if you have some n ciphertext that stores each row of given matrix, then that is equivalent to some matrix equation A times topless S plus B equals M. Okay, with this, now we can see how to reduce PCMM to PPMM. So I like this slide a lot. So let's assume that we are given a row-wise encryption of a matrix V. And our goal is to multiply a plaintext matrix U to this encryption. And all we have to do is just like multiplying the plaintext matrix U to the both end side. So once we expand, we have something like UA times topless S plus UB equals UV. So as I mentioned before, we can construct the encryption for the product matrix UV from this equation. So that means to do PCMM, all we have to do is compute UA and UB, which is plaintext matrix multiplication, and we can use BLAS libraries to do it very efficiently. So this is a algorithmic reduction from PCMM to PPMM, and for the good dimensions. So for other dimensions, please see the BCHPS paper last year, crypto. And okay, so now we want to do the same thing for CCMM. So maybe the most straightforward approach might be just do the same thing. But however, when we do the same thing for CCMM, here comes some weird terms like this. So here's some problem is that like for the first two terms, there's no PPMM. That's the first problem. And also the structured matrix are multiplied by the random matrix from the both left and right side. So the structures are kind of like destroyed once we expand this equation. So maybe probably it would be really good if we can switch the order of matrices. For example, like if we can switch this and this, then maybe we have like 4 PPMM as desired, and all the structures are kind of like preserved. So maybe this is a really good goal. However, this kind of like switching the order might not be easy because matrix multiplication is not commutative. So we need to figure out how to do it. Then to do that, let's understand what it means by the topless matrix at the left. Okay, so as I mentioned before, so top matrix on the right side is related to the row-wise encryption of matrix. And interestingly, actually the topless matrix on the left corresponds to the column-wise encryption of M. So you can understand it as like transposing the above equation. And so that means maybe to switch the order of matrices between the random matrix and topless matrix, maybe we need to do, all we need to do is something like transposition. So for example, so if we have large matrix like this, and if we're given some row-wise encryption, then all we have to do is make a column-wise encryption from the row-wise encryptions. So we call this a CMT, ciphertext matrix transpose, because it indeed is a matrix transpose. Okay, so in the limited time, I'm going to briefly explain how we can do it. So the most straightforward way to do it is to extract each MIJ, each entry of the matrices, and combine them back to get the column-wise encryption. So actually, it is known fact that we can extract each coefficient by n key switchings. We can do key switchings and sum them up, and we can extract each coefficient. So this directly gives some inefficient CMT algorithm. So we can do lots of key switchings, and we can do lots of addition to complete this CMT algorithm. However, this n squared times of key switching is not very desirable, as n squared time of key switchings means like n cubic bit operations, and that might be like even slower than PPMM itself, so it's not that good. So So we would like to reduce the number of key switching to n. So our idea is to share the automorphism as much as possible. So to do that, we just like do some equation, play with some equations. We swap the order of summation as all of their like finite sum, and it ends up with some interesting facts that mj prime, the column-wise encryption, is summation of this one, and this m sigma tilde is independent from j. Okay, so from this fact, what we can do is that from mi, so as this m sigma tilde is independent from j, we first just like compute m sigma tilde from mi, and after that we key switching each m sigma tilde. So here is like n key switchings instead of n square or n cubic key switchings, and from this m sigma tilde we can obtain the final output by another n square additions. So this just reduces the number of key switchings from n square or more than n square to n key switchings. So this is good. However, we still have some problem with these n square additions, because like n square ring additions means like n cubic bit operations, and that might be slower than ppmm. So however, the good fact is that the required additions are kind of like structured. So both additions are kind of like special cases of a general structured addition. And in the paper, we just observed that this kind of a structured addition can be done with like two subproblems with some extra additions. And we can solve the subproblem by subproblem and so on to get something like this. So at the end of the day, the total cost would be some linear ON bit operations plus n log n operations. So in total, we have like n square log n bit operations to complete this structured addition task. So to sum up, for CMT, we start with the row encryption, and we tweak, and we do key switching, and we tweak again to get the final column encryptions. So the total cost is O tilde n square. So asymptotically, this is negligible and minor compared to the cost of ppmm. Okay, so now we have all ingredients. So to put it all together, so let's see how we can reduce CCMM to ppmm. So we are given two row-wise encryption. So first we transpose the left term, and we expand it. So we have like 4 ppmms here. And we do ppmm to compute the matrices, and we swap the order of the topoless matrix and random matrices by using CMT algorithms. And after that, we do relinealization and rescaling to get the final row-wise encryption of the product matrix. So this completes the CCMM, and this is a reduction from CCMM to 4 ppmms and 3 CMTs. And ppmms can be done efficiently by using existing BLAS libraries. And for the CMT and relinealizations and rescaling, they're subcubic, so asymptotically minor compared to ppmms. Okay, so we also have some implementation. So in a single thread CPU, it takes like 1.5 minutes to multiply two matrices of dimension 4,000. And also we have some implementation for CMT, so it takes like less than a second to transpose a matrix of dimension 2,000 by 2,000. Okay. So to wrap up, in this work we have fast CCMM algorithm that leverage like high efficiency of BLAS libraries, and also we have some fast CMT algorithms. So in this work we mostly use CMT for as a tool of CCMM, but I believe that there would be like several application of CMT by itself. And also in the paper we have some lightweight algorithm that require only a small key size. So now the timing of CCMM is not anymore like tens of hours. So, and we have like less than 2 minutes to compute large ciphertext matrix multiplications. Okay, so our paper is available online. So thank you for your thank you for listening, and please feel free to ask if you may have.
Are there any questions? Can you explain a bit how you can compress the keys, have smaller keys?
Okay. So actually, in our algorithms, even though we reduce the number of key switchings into n, actually this key switching requires like all different key switching keys. So actually, in the basic algorithm, we need n key switching keys. So usually that might be okay because like we are in the very small parameters. So n key switching key even is okay for most of servers, but in our paper we present a lightweight algorithm. So actually in that algorithm we use a single key and we update the key right before we use the key. So that means we only have like one key and some keys for updating the key. So we have like 2 or 3 keys instead of n keys. So actually updating the key induces some overhead, but the key size is much better.
Thank you. No more questions? So thank you again for the presentation.